Okay, let's start for today. Good morning first. Today we have to do quite a lot. We have first to finish lecture of last time where we had the topic virtual substitution. I will give a small example in the beginning so that you can recover what we have done last time. And this was the last step we have seen in the last lecture. And then the exercise will contain Gomorrah cuts and omega tests. So we will have actually content of 3 lecture topics per week today. Okay, maybe, well, the task was that we wanted to solve formulas where the variables are of the real domain and the constraints can have something like, quadratic occurrences of variables, so nonlinear occurrences in general. Could be something like x times y or y squared or whatever. And the procedures we have seen before, like simplex or branch and bound, for example, they just could consider linear terms, so linear expressions here. The general idea was that we wanted to eliminate one variable after the other. So here we had first taken x for elimination, and then we got a formula which is equivalent to this one which we had before, but does not contain x anymore. So equivalence in the sense of having a solution in the reals. Okay? We have seen that we needed something like a finite set of candidates which we could put inside or where we could replace x by, and we check for each of the 10 candidates if it holds, and if it does not hold, then we check the next one, and if there's no one which fulfills this formula, then we know that it's unsatisfiable. The candidates we constructed by considering where and which constraints the variable we want to eliminate occurs. So here there are just 2 constraints, and for each constraint we could construct the test candidates. And this was done by, let's take a look on this slide, considering the relation symbol. So you see here we have weak relations or equal. Here we could take directly the 0 of the polynomial as test candidates. So of course it would fulfill this constraint itself. And minus infinity, which means actually just a very small number. It's representative for a very small number. Okay, for the strict ones, so for not equal or smaller or greater, there we had to add to the 0 in infinitesimal, which is just a very small number. That means we have here the 0 plus some infinitesimal, so a number which is very close to 0, but greater than 0. Okay? And again, minus infinity. So for this example here, we have seen that the 0 is minus 1 divided by y, and there is one thing missing. If we put y in the denominator, then y must be greater than 0. Not 0, sorry. So this is a side condition which also has to hold. And in this formula, you can see that we construct it by, well, we take the 3 test candidates we can get for these 2 constraints containing x, and then we replace x by the test candidates. How we replace it, we will see later. This is the content of this lecture today. And if there is a side condition, we put the side condition in front of the resulting formula after substituting. Okay. Some questions left so far, because I would like to give you a small example where the substitution is not that difficult. And maybe you see there how it works. Oh. Okay. So let's take x minus 2 is greater or equal than 0, and x times y plus 1. This one you know. less than 0, less or greater than 0, and y should be greater than 0, greater or equal to 0, sorry. So this is just a conjunction now. We cannot solve it with simplex because you see there is one nonlinear part inside. Okay, so we choose now first a variable for which we want to generate the test candidate. So the variable we want to eliminate. So let's take here x. Oops. First to eliminate. And for x, we have two constraints containing it. So the test candidate would be, or in general, always minus infinity is 1. Then we have here, we have 2 as a 0 of x minus 2. And for the last one, we know already minus 1 divided by y. And here we had the side condition that y is not 0. Okay, so this is nothing new for you. Let's now substitute. I will not show you how to do it exactly now, but just give you an idea of how to do it. Maybe you will understand it. If you take minus infinity, for example, well, if you take a very small number, so you can always find a small enough number that satisfies this constraint, where you can easily see that if y must be greater or equal to 0, this would not fulfill this constraint. Yeah, this is the idea of minus infinity. You can always find a small enough number fulfilling this constraint. But if we take minus 1, well, then it's already not fulfilled. So this constraint, y greater equal 0, is conflicting with this test candidate. Yeah. So actually it would be, the substitution would lead to, so it would look like this, just for this constraint now. If we substitute x, wait, sorry, wrong constraint. There's no x inside. This one, of course, yeah. So x minus 2 greater equal 0. So if you take minus 3, for example, then this would already not fulfill this constraint. So there's no sufficient small number to find always. So if we substitute, it would look like this, minus infinity for x, and it would just be replaced by, so this is actually an equivalent symbol to false. Okay, and if we put false here, if we replace it by false, the remaining doesn't matter. We have a conjunction, and conjunction and false is also false, you know, satisfiable. Okay? Did you see this a bit? Okay. So let's take the next one. It's 2. So for 2, well, of course it's fulfilling the first constraint. It is 2 times y plus 1 is 3. Less or equal than 0 is wrong, yeah. So we have already here conflicting constraint. So x times y plus 1 less or equal than 0. We apply the substitution on this one. It's also getting false.
When did you say y to 1?
Oh, I'm sorry. You're right. The y is still there, yeah. So we have y plus 1. So equal 0. Okay? Yes, of course. But I just wanted this one. Sorry, yeah. Okay. So, well, we replace just x by this number 2. 2y plus 1. Thanks. And we have y greater equal 0 left. There's no x inside. So this is our result. Yeah. If we have this formula phi, then this would be the result of substituting y by 2, x by 2, sorry. We get, yeah? So there's still y inside. Now we have to eliminate y. So for y, we get the test candidates. Well, for the first constraint, we have 0 is minus a half. Am I right? Yeah. So, and for the second one, it is 0, and of course minus infinity. I forgot. Yeah. So minus infinity. Well, minus infinity is conflicting with y must be greater or equal to 0. Yeah. And let's take next minus a half. Well, minus a half is conflicting also with the same constraint. Yeah. And then we have 0 is conflicting with the first one. Yeah. So if you have 2 times 0 plus 1, 1 less or equal to 0, then we have conflicts. So you see all the test candidates did not fulfill. So here, that means actually that that elimination of x by 2 fails. Yeah. And I'm not sure if I can give you an idea of why this fails. Well, let's take the next one, the last one. We have now minus 1 divided by y. So here, it's getting a bit more complicated now. Well, if we would replace just x by 1 divided by y, minus 1 divided by y, this would lead in the first constraint to 1 divided by y minus 2 greater equal to 0. Just substituting in the common sense, yeah? Just replacing it. Well, this is not our logic now because we don't want to have division in our constraints. There's just multiplication and addition allowed. So we must transform it somehow. Well, if we would now multiply by y, yeah, we could get something like 1 minus 2 times y. But the problem is, what is the relation symbol here? And it's not that clear. So if it is greater than 0, yeah, we get, I'll write this down this line directly. So if it is greater than 0, well, the relation symbol is not changing because we multiply by a variable which is not smaller than 0, so the relation symbol here will keep. Hence we get 1 minus 2 times y greater equal 0. Okay? So the other case would be, of course, that it is smaller than 0. It could not be 0 because of the because you can't divide by 0, of course. And then the relation symbol would change, and we have 1 minus 2 times y is less or equal to 0 instead. So this is just what we get for the first constraint, substituted by this test candidate. So for the second one, well, this is obviously just fulfilled, yeah. So it could just replace it by true, because we have y divided by y is 1, plus 1 is 2, is minus, sorry, it was minus. So we got minus 1 plus 1 is 0, so 0 is less or equal to 0. So this one would be fulfilled. And the last one has no x inside, so we can just keep it. And what is missing? Yeah.
Should we have minus 1 over y?
Minus? Here?
Yeah.
Yep. Yes. This would change this. Right. Okay, I hope this will not change very much. Well, what is missing is the side condition. Yeah. Because we can just have this test candidate under the side condition that y is not 0. Oh. Okay, so this is what we get. So now let's take a look on the test candidates again. Now we can eliminate y here. And this results in, well, take the easy ones first, minus infinity, of course. I put them, minus infinity. Then we have, for this one, we have 0. And then for this one, we have plus 1 divided by, is it right? Minus 1/2. Right, so 0 of this polynomial here. The same for that one. So we can just omit it. And finally, we have also three strict constraints. And for all of them, it's the same test candidate. It's 0 of y, which is 0, plus infinitesimal. Oops. Okay? Okay, so let's check now first 0. For 0, well, it would, let's go from left to right, it would not fulfill the first constraint, so false. It would, is it right? Minus 1 greater or equal to 0 is not fulfilled. Then we have here, again, false, not smaller than 0. And here 0 is, minus 1 is smaller or equal to 0, so this is fulfilled. So we have here an and, an or, and here we have finally one fulfilled constraint and one not fulfilled constraint. So at all it would be not fulfilled because just of this one. Yeah. So if you take another one, minus 1/2. Well, for 1/2 it worked. I hope it will work for minus 1/2. So for the first constraint, it is not fulfilled. The second must be fulfilled because it was tested of this constraint, which is not always the case. Yeah. So if you have a test case of constraint, it does not mean it must fulfill it. For example, y is less than 0. Yeah, has test case 0 plus epsilon, and of course, if you take a value which is positive and you need it here negative, then it's not fulfilling it. Okay, so here we have false and true, or minus 1/2 is fulfilling that one and this one. And finally, we have, well, it's not fulfilled. That's bad. This one is fulfilled. So again, this would lead to conflict. What is missing? Minus infinity. Well, minus infinity is not fulfilling because just of that one here. Yeah. Down this way. And finally, we have 0 plus epsilon. Oh, this is hard to read. Okay, 0 plus epsilon is fulfilling that constraint. And, well, it is, if you put 0 inside for y, yeah, so I'll give you just an intuition of how it works with epsilon. So if you put here 0 inside, well, you would get here minus 1 plus, minus, because here's minus, some infinitesimal. So minus 1 and a bit less is not greater or equal to 0. Of course, yeah. So we have here 2 false. Then here we get, oh yeah, right, yeah, 0 plus epsilon. And here we get now a false, and here we get now true, because of the same reason. And finally, finally we get here true, and here also true. So at all it is again false, because we have here one false, that's false, so false or false is false, and something else is false. So you see, this should be not satisfiable.
I'm still not sure about the choice of the state. It has something like y smaller than 0, then I have 0 plus epsilon. And if I have something like y greater or equal than, y plus 1 greater or equal than 0, then I have minus 1 as candidate. Isn't there exactly an interval between minus 1 and 0 that just does not have any candidate?
So wait, this, once again,
So that
y is
strict y greater than 0
and
y plus 1 smaller or equal than 0.
smaller or equal to 0. Okay.
So then I get 0 plus epsilon.
Okay. Yep. 0 plus epsilon.
And minus 1.
And minus 1 exactly. And minus infinity.
And minus infinity.
Yep.
But should there any test candidate between 0 and minus 1?
It is. 0 plus epsilon. This is a testing candidate which is between 0 and minus 1.
Can epsilon...
Minus 1. I'm sorry, no. No, of course not. No. There's no. But if you would put this in the number line, then you would have something like, if it's 0, and we have minus 1, sorry. Then we have, for the first, this interval. Yeah?
Yeah.
Then for the second, it is that interval. Is it right?
Yeah.
Yeah. And, well, there is no solution between those two, but the splitting of this intervals from the number line, yeah, looks like that there is here actually a weak bound. Yeah.
Yeah, sure.
So this weak bound this is actually a trick. Well, usually you could do it always the case that it's not weak, that it makes strict, and then you have to consider, of course, minus infinity for this one. Then you have here minus 1 plus epsilon for that one. And then you have, for this one, finally, 0 plus epsilon. And, of course, for the things in between 0 and minus 1. So this would be the straightforward approach. But here, if you take the weak bound, you know that it's contained by this interval, yeah, this one here. So minus 1 is actually the test candidate which replaces, or which is a representative for the first, here this first part, yeah, of the timeline. Then minus 1 represents this part, and 0 plus epsilon the remainder. And this is what we have heard about this invariance, sign invariance, and so on. So
how can minus 1 be a candidate of the inner interval if it belongs to the left interval? Yeah, minus 1 fulfills the second constraint, but minus 1...
Right, and this is another thing which last time didn't get through, I think. You don't know the direction of this endpoint.
Is a representative of the first interval.
It is not. It's actually for the second one. That's it. I mean, it's...
But then
if you have, now you have here just one variable inside, but if there's another variable inside, yes, then this could lead to that the relation symbol is changed. So, for example, for, let's say, if we have this x times y plus 1 smaller equal 0, so it depends on the value of the x, yeah, if it's negative or positive, how this relation symbol in the end is looks like. So if it is negative, yeah, it would change, and then it would, for example, here it's not exactly this interval, but it would be this way, yeah, and then it's right, and it's indeed in this interval, but it's actually for both directions in this interval. You see, doesn't matter.
But the whole idea is to partition
Right.
that all numbers in one interval are all greater or lower or equal to 0, or the function of this number.
That it is it should be the number of an interval, so one of the splittings, and we need just one for each splitting. So if we have here a splitting of, we have 3 splittings here, and for each we need one representative.
So the original question was, why are we guaranteed that the interval between -1 and 0 in this example is not satisfiable?
Because
so obviously you have no. So basically you are saying -1 is a test candidate for the interval from -infinity to -1
right.
and -1 to 0.
No, just for -1 to 0, containing 0.
But -1 is for the second constraint is fulfilled, but any other number in this interval will not fulfill it.
Right, but it's enough for this conjunction. So we have the first constraint, y is greater than 0.
The first interval from -infinity to -1, because they are all numbers within the interval behave the same with respect to this second constraint, right?
Yes, but the thing is, we want just one representative for each splitting. And I don't know, what do you mean by that? What you said?
We want to select our interval such that all numbers within the single interval behave the same for all constraints.
No.
Okay.
We want to have if we have just one variable here, and it's better to consider it this way because it's getting really nasty otherwise. But it doesn't matter how many variables are there, but in the end, there will be for one variable a splitting of all this time of this number line, yeah. And it looks, for example, like this. And what we want is that for each part of the splitting by the intervals, there is one number inside, and this is a test candidate. And well, if we check those test candidates, one after the other, and there is non-empty part of the splitting, then would fulfill this, yeah? So you have to consider again, you have had this intersection of a set of intervals, and there must be a non-empty interval such that there is a solution. But if we have for each splitting, so for each interval actually one candidate, then we can just check all these 10 candidates, and if there's a non-empty one inside, non-empty part, then we know that we get our result. So,
but then there are candidates that will work, and within an interval there are numbers that work and numbers that don't.
Of course, but you have just one number for each part. I don't see.
Yeah, but so how are you sure that you select a number that will work?
This is a procedure. No? The procedure says that this number is a unique number for this, or a representative number for this interval, for this part. Yeah.
I don't understand anymore. What do we want to achieve with the partitioning? So we partition the space, and so we put real numbers into some category.
You have the
real numbers in one interval have in common.
So you have one. Let's just consider one variable. Yes. You have in the end you have partition like here above. Yes. You have something like this. Interval like here, yes, there, this, sorry, and so on, yeah? This is always the case. And, well, if you have two constraints, here could be some other constraint, yeah, like this one, and so on. Doesn't matter how many intervals I make here now, yeah? In the end, we have a partition of these endpoints. And for each of these parts, we know one number inside. So if there's one non-empty, that means this number is also a solution. Yeah, if one part here means a solution, yeah, all this, it doesn't mean that all these numbers inside this part are solutions. And this is also the case for the number we choose. So for each part, we choose one number. This is the procedure gives us this number. And if there is non-empty, or if there is a solution interval here, a solution part, then this number is fulfilling it. So the constraints, yeah?
What we say in the end is, if we have a test candidate for an interval and the test candidate fulfills the formula, then every number in the interval will fulfill the formula.
Right.
But that's not the case. -1, or -1 will at least...
There is no solution, so there is no solution interval. I don't get the point.
But shouldn't it be the case for each constraint too? So if a number of an interval fulfills...
Just one constraint. So you mean just...
Constraint y plus 1 is lower than 0.
Right? So it's just... this one, yeah?
Yes, so -1 belongs to the lower interval. For minus infinity...
Does not. It does not. Belongs to the next interval. So the thing is, you consider the direction because you have just one variable, yeah, and it's clear that the direction is like this. But it's not that clear if you have more than one variable. So just take this information. It is not belonging to the first. It's belonging to the second. Okay?
But then it's the only variable in the second interval that fulfills the constraint. All others
it's not.
don't.
Wait. It's both fulfilling now. Yeah. That's right. Well, in this case, you're actually right because it's the one which fulfills and the other not fulfilling. Then it should belong to the first part, right?
Okay.
That's right, but it's not making it less satisfiable. Yeah.
Yeah, and then to my original question, if -1 belongs in this case, in this special case, to the first
Right.
Interval, then we have no representative for the interval in the middle between -1 and 0.
Yeah, but in this special case, you don't need it.
Yeah, but so the procedure always guarantees us that if we don't have a representative, we don't need one. So it's
more or less, yes.
That we have intervals where we don't have a representative.
Right. But if, just considering what I have told you before, actually it should really be, this is more or less making it easier, yeah? So the algorithm more efficient, but it should be something like this, yeah? We have here an open interval, open left endpoint, a point, and the open right endpoint. And then we would be right, because here we would take plus epsilon, the point itself is its own interval, and for here we have minus infinity. Then everything is fine, yeah? This would make it a bit more clear, I guess. But this, this weak bounds here, they are giving us some advantages which we want to use. That is all. Yeah. Okay? Okay, now I've lost a lot of time. Okay, but I think you have understood more than I expected you to understand until here. So we can maybe go a bit faster through the next slide. So as I told you, if you substitute in the common way, and we have terms substitute such that these terms contain epsilon or infinity or square root, or there is a division inside, then it is giving us a constraint which is not in our logic because it contains, well, new variables actually, or square root or division. And we know that the reals or this logic of real algebra just allows us plus or times. So we need some rules, as I have showed you in the first example. I have made some rule there. And these rules give us actually equivalence expressions in real algebra, which do have the same satisfiability behavior than the expression we had before, yeah? But with one variable less, of course, namely the variable we want to substitute. Okay, and I give you now two examples just to give you an idea of the rules. So the rules are 5 pages of nasty real algebra stuff, so you don't want to see them. But in general, there are ideas behind these rules, and the ideas you can, let's say, summarize with these two examples. So the first example is already kind of general, and because we have here now a general kind of test candidate. Yeah? So Q plus R times a square root expression divided by something, and S, R, and Q, and T are all polynomials. So if you reconsider how we get test candidates, We get it by solving the equation for a quadratic equation, for example, or a linear equation. And in the worst case, it could look like this. So if it's linear, r would be 0. If it's not linear, if it's quadratic, it would indeed look like this here. For the first root of a quadratic, it is a negative. For the second, positive, and so on. Yeah. So this is a general, 0 we have here, but no plus epsilon, of course. So what if we substitute now? Well, this is the result, you see. I just give it here, but I will explain later why we have this result. So if we substitute now x by this expression in a polynomial g, in some polynomial g which contains x, then I can transform it later to an expression which looks like the expression we had before, but of course with new q, r, and s. So q hat, r hat, and s hat, and the t keeps being the same. You can maybe prove this as an exercise. It's not that difficult, but it is possible. If you make addition of two such terms, you can transform it back to such a term, and by multiplication it's the same. Okay, so hence we can take now the result. Yeah, so we substituted x in g by this expression and get this as result. And now we have to compare. So what is? Well, it must be 0. We know this. What if r is, or r hat is 0? Well, then this term would be 0 here. And hence we have q divided by s hat, q hat divided by s hat equals 0, and r equals 0. And well, if we have a fraction being 0, then it means that actually the enumerator must be 0. That s is not 0 is also part of this test candidate, yeah, that this side condition holds, but in general it holds as well. Okay, so we can just get rid of this denominator and we get finally this result. So r is 0 and q is 0. You see here it is the first case of our rule. So if r now is not 0, and this must be 0, that means, well, we have something here and something there. Now, we can get again rid of this s because it is a denominator which is not 0, and this numerator must be 0 then. And finally, we can produce this formula, which means, well, the absolute value of q and of q hat, sorry, and r hat times square root of t must be the same if r and q have different signs. Of course, yeah. If this is the same amount than this one, if this is a minus actually, then you know this is 0. And otherwise, well, r times q should be 0. Yeah, if both are 0, oh, well, if both are 0, which is actually not allowed, then this numerator is also 0. So you see it is a bit superfluous. But it's always better to keep less or equal or greater equal instead of less or greater because of this epsilon. Epsilon is a good thing, but it's making it more difficult. So substituting by something plus epsilon really blows up the formula. But the other ones, the easy test candidates, I'd say, they are quite fast for the procedure. Okay, so questions until here? You see, it's just comparing, yeah, and you get this rule. So next is giving you more an idea of how this epsilon works. So we want now to substitute this constraint, or x in this constraint, by some expression plus epsilon. And now we have three cases. And to understand these cases, we take a look at the graph of gx, the function graph plot. Well, the first case says, well, if we replace instead of e plus epsilon, just e by x by e, and this is even smaller than 0. Well, because of the density of r, there must be a number which is very close to this e, which is also negative. So in R, we can always, the density of R is infinite, and we can always find the number close to it. Yeah, so we know this is here negative, and this here these three plots show us the three different functions we could have for g. So quadratic, linear, or constant. And the result of e is negative all the time here, yeah. And if you take plus epsilon, so very close to e, still negative, okay, because of the density of R. Then if we have that it is 0, yeah, then we take a look at the derivative of g. And in this case, we have not a constant function anymore, of course, because it's less than 0. And we have these two cases. And if the derivative in e is negative, it means we go that direction. And that means if we have e plus some infinitesimal, it must be under this line of x. So it must be negative. Okay? And finally, well, the last case just holds for quadratic functions g, where we have that the first derivative is 0 and the second one is negative. And then it looks like this. And here you see again, if we take e plus some infinitesimal, then it would be here negative again. Okay? Okay, I think, yeah, this example I can't make anymore, I think. So any questions left until here for virtual substitution? We will have an exercise for this, and next week we will have another example. And maybe I can have some more time, but this example is not giving you more information than the example we have done in the first part of the lecture. And what I can give you is the complexity. So the complexity, yeah, this is not a very nice complexity analysis, but this is from the paper of this virtual substitution. And what you can see of this is that it is exponential. So this is one elimination step, giving us a polynomial complexity. And if we make several elimination steps, so for all the variables, to get rid of them, then we have a complexity which is exponential in the number of variables still. But there are differences in exponential complexities, namely that it could be single exponential or doubly exponential, and in this case it's single exponential complexity, and for the cut approach, for example, this is double exponential. So it's much slower in practice and in theory. Okay? Okay. So let's finish lecture now and let's go to the exercise.